Okay, we're going to continue where we left off. So with the force of friction, it's always going to oppose motion, depends on the type of surface and how hard they are pushed together. So with that, the force of friction has an equation as well, where the force of friction is equal to what we call the coefficient of friction times the normal force. Remember that all of these are in units of newtons. So in this case, our F is the force of friction. This mu is the Greek letter mu. Okay, and it represents the type of surface. So that type of surface, you could have ice and the rubber tires, you can have water and ice together, sandpaper on wood. So we have to somehow put that into our equation, and that's what that mu represents. It is just a number. That number will change depending on the surface. Of course, the higher the number, the more friction is. We already said what the Fn is, and that is the normal force. Okay. So those are the equations. This is your equation to find the force of friction. So what I'm going to do now is that I didn't like our drawing that we had at the beginning all the way up here. So I figured out what I can do and to shut that all off. So I'm going to redraw right in here just to add to your notes. So you should have the same thing. But we have our surface, right, that doesn't move. On that surface, we're going to put our box. And so far we have three forces, right? So we had the force of gravity or weight acting straight down. Our normal force was acting straight up. And that is perpendicular to the surface. The force of friction opposes motion. So to be able to describe the force of friction, you have to, off to the side, say which way do you want the object moving or which way do you think that it is moving. So if I choose motion to the right, friction would be to the left, and it'll be between the two surfaces and oppose motion. So it's always in the opposite direction of motion. So that's our force of friction. So if we can slide back up here to our notes, it opposes motion, depends on the type of surface and how hard they are pushed together, and also is parallel to the surface between the two objects. So those are our three forces so far. Three most important forces that are very hard to ignore for the most part. All right, the next one we often do ignore because it's a changing one, but it is another form of friction, and it is air resistance. So this is going to exist in your system if one object, or I should say the object, is moving through the air. For this one, we are going to ignore unless mentioned. First, this variable, we're going to write FR. You'll see why, because I'm going to do an applied force. This is for air resistance. And it's very similar to friction. It opposes motion. It is a form of friction. Right? Opposes motion, so it's always in the opposite direction of motion, But in this case, it does. Depends on speed and surface area. I think I need two S's up here. Sorry about that. All right. Opposes motion. So because it depends on speed, the faster an object gets, the more air resistance there'll be. So it's actually a variable that could very possibly change within your problem if you're accelerating. So until we get really concrete understanding of Newton's second law and how we put all these forces in, for the most part, we are going to ignore it because it changes. But I will show you some demonstrations with that regarding air resistance so you have a better understanding of that. But that's what we want to take a look at. We can't ignore it because it exists, but again, it's a changing variable, so it's sometimes hard to account for it. So the next one is often present when you have a rope, string, or cable. So the system that's involved is a rope, string, cable, chain, any one of those things on your object. We're going to call this a tension force.
May I please have your attention for the afternoon announcement?
For our tension force, the tension force can only pull,
Brooke Simon, Madison Kerger,
cannot
Ellery Team,
push on an object.
Katie Larkin, and Cohen Atkins. Let us pray. In the name of the Father, Son, Holy Spirit, amen. Dear Lord,
As long as the rope,
my mind, or my focus. Your love is limitless like the infinite sky.
chain,
I pray, amen.
cable,
The Father, Son, Holy Spirit,
etc., remains tight and doesn't break, tension is constant throughout. So what I mean by that, if two people are pulling on a rope like this, right? And they both pull on it, as long as that rope is tight, then when this person pulls, there'll be a tension that way, and on this one, the same amount of tension. Anywhere in there, there'd be the same amount of tension anywhere within that rope. So to add that to our picture, we need a rope, chain, or cable. So I'm going to assume that it's moving to the right because I attach some kind of rope, chain, or cable to it, and we'll call that a tension force. Okay, next. This is what I was talking about in that all forces are applied. Sorry about those announcements. All forces are applied forces, but in this case, I'm going to call this an applied force, but it's due to another outside object or person in direct contact. With the object you are looking at. So I'm going to call that a force applied. And again, all of these forces are applied to the object, but this is the force that's going to come from my hand touching it, another object bumping into it, something like that happening. So we call that the force applied. Not really anything to say about it. Usually it's a push of some sort. So I'm just going to say usually. And that just gives you for your direction. It's a pushing force. It'll push on things. Okay. So again, that's due to another person, another object. So if I go back up here to our picture, let's say somebody is standing behind this block. Right? I want to come up here and I put a person in here pushing on this. They might apply a force in that direction to cause it to go forward. So those are your main forces. And I sum it up by saying any other special forces, right? So your last force is the system would be anything left out. It could be electrical, magnetic, could be a thrust force, could be a buoyant force. Okay, and I just call that your special force. So we're just going to label it an F. But honestly, if you have that, you would subscript it with one of these letters to represent it. Notice that it's really that all that we have to make sure is that we are accounting for every force and we're going to label them differently. So we're going to ask ourselves at the end of drawing our pictures, is there anything else that could possibly be there? And this is what I mean by this at the end. That's what I want you to ask yourself. So as you're drawing your picture, any other special forces? Could there be an electrical force? Could there be a magnetic, a thrust, a buoyant, and so on? Okay, so in that case, you just determine all of that information, direction and magnitude, based on your problem. So what we're trying to do here is I have given you a list, I believe, of 7 forces that we want to hold ourselves accountable to going back and being able to draw a picture and decide which one of these forces would be present. Okay. So of all these forces, we want to be able to go back and say which of them would be present in our problem. Okay. So I want to list them independently here. So going back to all of our notes, if we were to go back and eliminate the extra notes that went with this, our types of forces are, number 1, weight, which is due to the force of gravity. 2, normal force. 3, sliding friction. And we're going to we'll do a whole lab on sliding and static friction. So static is when it wants to slide, but not quite sliding. Sliding friction is when it is actually sliding. But overall, that friction, air resistance, tension, applied force, and then any other special forces. Okay. So again, you're going to draw your object, right? You're going to ask yourself, does it have weight? And if your answer is yes, you're going to put weight on the object. You're going to ask yourself, does it have a normal force? If the answer is no, then we don't put it in. It's not sitting on anything. If there is sliding friction, you're going to ask yourself, would there be friction? If the answer is yes, you put it in. If it's no, you keep it out. You ask, is there air resistance? If the answer is yes, we might put it in. And first, you have to decide which way it's moving. And then air resistance and sliding friction always oppose motion. So maybe I would add my air resistance in. Is there a tension due to a rope, chain, cable, or anything like that? If your answer is yes, so maybe I have this, I'm lifting something up with a chain. So then I have this big tension force that might be lifting my object up. Is there any other applied force? Maybe somebody's hand is underneath this object holding it as I lift it up. So in that case, oh, maybe I do have an applied force coming up from the bottom as well, right? Any other special forces mentioned? Are there any magnets involved? Any electrical things? Anything like that? And if I say no to it, I don't add it. If I say yes, I add it into my picture. Once I'm done with that, then what I really want to do is go back and clean up this quick picture that I sketched. I then want to go back and just draw a dot representing my object. And then I want to draw all forces originating from that object. So I would have tension, right? Air resistance, all acting in the same direction. Force applied. And then weight. And this would be considered your free body diagram. Often called FBD. So again, you ask yourself what forces are present, yes or no, you put them into your picture, you clean up the picture and draw a final one with all forces originating from what you might think of as the center of gravity of the object. So we'll put in rotation and stuff at another time, but this is it. This is for static equilibrium or motion, doesn't matter, but that's what we're going to evaluate. What is the effect of all of these forces acting on one object at the same time? How is it going to cause it to move according to Newton's second law? Okay. When we do that, then we would have to go back and ask ourselves, which way would it accelerate? Would it accelerate? How much is it accelerating? So once we master these drawings, we can answer those questions, right? So that's it. We will come in tomorrow and practice these drawings.